Last video, 4 more hypervalent species, XeF4, one of those fascinating noble gas compounds. Obviously doesn't obey common sense, because common sense would say xenon doesn't make any bonds. So 36 valence electrons, 7 each from the fluorines for 28, 8 more from the xenon, and xenon in the middle bonded to the 4 fluorines. Again, students who are just rushing through would just say, oh, that's nice, look at that, 4 bonds, everything's got to be fine. Count the dots. 32 dots. Thus we need 4 more electrons, thus the xenon needs 4 more, which come in as 2 lone pairs. Xenon, the central atom, 6 groups of electrons, 6 groups octahedral. However, there's only 4 bonding to a lone pair. What then we do see? In this case, if you think of the original octahedron, we've removed what would effectively have been the axial positions, the way that we drew it at first. So top and bottom removed, lone pairs at 180 degrees to each other. Lone pair on the top, lone pair on the bottom. Now, I emphasize top and bottom because those lone pairs cancel each other out. The top one pushes them down, the bottom one pushes the bonds up, thus pushing up, pushing down equally cancel out. The angles are exactly 90. And because those lone pairs cancel out, this is one of those very rare examples where you have an atom with polar bonds and lone pairs, but it's not distorted, so it's non-polar. SEF4, again, one that is wonderful trap for those people who don't think about what they're doing. Draw it like that, it looks beautiful. Count the dots, 32, we need 34, and so we need to give the selenium an extra lone pair. Selenium has 5 groups of electrons, 5 groups, trigonal bipyramidal, 4 bonding, 1 lone pair. So we take a trigonal bipyramid and we remove one of the equatorial positions and replace it by a lone pair. So we get the seesaw or sawhorse or diphenoidal shape. I can't even pronounce the silly word. So anyway, we look at that. The angles used to be 120 between the equatorial and 90 between the axial and the equatorial. But of course, we got a lone pair distorting those. So it's going to be less than 90, less than 120. Back to the usual situation, lone pair on a central atom that has polar bonds, distorted polar. Last stretch, another interhalogen compound, ICl5. Obviously no common sense, 42 valence electrons, iodine in the middle. You'd stop there if you're not going to count, but if you do count, you think 40 dots, we need 42. Iodine gets another lone pair. 6 groups of electrons, 6 groups we've already seen octahedral. Only 5 bonding, 1 lone pair. So we remove one of the positions on an octahedron, and it doesn't matter which one we remove, we always end up with a square pyramid, an equatorial square and then a capping axial position. Angles start off at 90, got that nasty lone pair distorting them, so less than 90, and thus of course would be polar when you have that distortion and polar bonds. Finally, XeF2, getting no common sense. Xenon 8 electrons, 2 fluorines 14, gives us 22. Xenon in the middle. Look at that, you think that's nice, just like water. Central atom with 2 bonds, 2 lone pairs, you'd say it's going to be bent. Unfortunately, it's only got 20 dots, you need 22. So that poor xenon gets another lone pair. Xenon central, 5 groups of electrons, 5 groups trigonal bipyramidal. But now we've got only 2 bonds, 3 lone pairs. What do? Well, it becomes linear because we just put lone pairs in each of the equatorial position. Now when you've got that, those lone pairs again cancel each other out. So the angle is exactly 180, and because those lone pairs are cancelling out, there's no distortion. It is a non-polar molecule. As I said in the first movie, went through this rather quickly once we went through a little bit of detail in the first movie. Any questions that you're not sure about, feel free to email me.